the sixth session of the seminar on meta theory of type theories. I will try to share my screen now. Okay, can you see it?
Yes.
Yes.
Okay. So yeah, as a reminder, last time the main topic was identity types in type theory, which is a pretty big topic. And today we will look at some new model construction that we have not seen before. And in particular, we'll start by the family model. Maybe I can. So previously we have seen the initial model or the syntax of type theory, and we also have seen the set model, also called standard model. And the standard model is the usually when we write things in type theory, we intend to interpret them in the standard model. And again, now we look at the family model that is, in some sense, some generalization of standard model. So it can be seen as a part of a larger family of models, Redshift models, and the standard model is also a Redshift model. But it's a very simple Redshift model and it's easier to describe it directly instead of describing it as a Redshift model. All right, so in the standard model, contexts and types are interpreted as sets, but in the family model, contexts and types are interpreted as families. Where a family, so there I defined the contexts in the family model, and a family consists of a base set and a family of a fat set. And somehow all of the components of the family model are tuples with are pairs of an element somehow in the base and an element in the family. And well, maybe again, I don't know. The components with 0 will be given exactly in the same way as in the set model. Okay, so here I have defined contexts, substitutions, types, and terms of a family model in Agda. So the context, a context is given by a set, gamma 0, just like in the standard model, and then a family of a fat set. Maybe you can skip substitutions for now. Well, no, and look at types. A type is given by a family over the first element of the context, just like in the set model, and then some family of sets that depends on both parts of the context and the first part of the type. Then substitutions are given by a function between the first part of the context and some dependent functions between the second part of the context. And terms are given by a family of elements. So terms of a given type are given by a family of elements of the base type of the type over the first part of the context, and the family of elements of the second part of the type, depending on the second part of the context. And yeah, so there's a question.
Sorry, maybe it's helpful for intuition to think about sets and predicates. I don't know, or I don't know. It's confusing, but because then you can say that maybe functions which respect the predicate. Yeah, I don't know.
Yeah. Well, yeah, I guess we could look at a subclass of contexts and types where the gamma 1 is a predicate on gamma 0, and then and A1 is a predicate on A0, and then the second component of types and substitutions says that the first function respects the predicate. But I don't know this. Maybe this can also be a bit misleading. Right. Well, and then everything in this model will be defined somehow pointwise. First, we define it for the first part of the context, substitutions, types, and terms, and then for the second part.
Hey, can you guys hear me now? Because I was trying to...
I can hear you, yes.
Okay, so because previously I had someone telling. So your previous point about interpreting gamma 1 as a predicate. So if we push on that, what we get is the context is basically a subset of a set, right?
It's a set equipped with a distinguished subset.
Yes, and then a type is another subset, because A0 is another subset of the same set, right?
No, A0 will not be a subset, and types will not be. So we would have we would have gamma 1 in prop, so gamma 1 would be a subset of gamma 0, and the same for A1, but we will still have A0 in set usually.
Okay, I see. So we can't really give A1 some kind of subset like 7. Well, I guess A1 is then going to be a subset of
A1
pairs.
is going to be a subset of the restriction of A0 to gamma 1.
Okay.
So A0 is a family over gamma 0, and A1 is a subset of the restriction of A0 to gamma 1.
Okay, cool.
Okay, so let's define some. Well, okay, so we could define the whole substitution calculus and give this the structure of CWF. So we can define identity substitutions, the composition of substitutions, the substitution operations on types and terms, and so on. And while this it follows the same structure as in the standard model, maybe I can at least give a definition of extended contexts. So okay, then I need to introduce sigma types in the meta theory. So just okay. Okay, and then how is this context extension defined? Well, the first component is the set of pairs so this is the set of pairs of gamma 0 and A0 with gamma 0 in gamma 0 and A0 in A0 of gamma 0. And the second component is the family over this previous set of the pairs gamma 1, A1, where gamma 1 is in gamma 1 of gamma 0, and A1 is in A1 of all of the previous things. yeah, so I don't know if the Agda syntax helps everyone, because I don't know if everyone is familiar with it. But so we can define the whole substitution calculus, and then you can also define some types. So maybe let's look at the VMT type. It's a type, and you can also define the empty context. Or we can just say that the empty type is a type in any context. Okay, and well, so the empty type, the first family of types will be a family of empty types. So we need to define the empty types of our meta theory. So this is the empty set, and now we define this the empty family. And what happens is that the first component is the empty set, and then the second component should be a family depending on this empty set, but yeah, there's only one such family. Then you can also look at the unit type. Again, first I define this unit set in Agda. And now the unit family is defined. So both components, the first component will be the unit set, and the second component will be the unit family of sets over the unit set. Okay. Maybe as a last example here, we can look at booleans. In this model, and yeah, this should be either. I could hear some microphone, but
yes, I wanted to notify you about the recorded data.
Okay. Okay, but now this family, we need to define it by pattern matching on X. So not sure if is it possible to, yeah, maybe we can. I don't know how to pattern match things in line like that. So Okay, and it does not depend on the context gamma. Okay. Well, actually, this family is defined to be. Well, we don't need to depend on x because we can just define it to be constantly 1. So.
But also, doesn't the unit record need a constructor?
You don't need to specify one, but we can.
Sorry.
We can give it a name. If we don't specify constructor, then the only way to define it is to write record. Is to write an empty record.
Oh, I see.
Or you can also write an underscore.
Yes.
It always works.
because this has one only exact. This has exactly one element. Agda knows it, so. Yeah. Okay. So here it's a bit interesting for the family of Booleans, because the choice between true and false is made in the first in the set and not in the family. In the family, the information between of the choice between true and false is already made in X. So we will always. So we don't need to add more information in the family, and we can check that this satisfies the induction principle of Booleans. But then we can also, well, I guess more generally, we have, so if we have, any type, so if you have any context gamma, and then some type, but not of the not on the family model, but of the set model. Okay, so any type of the standard, any type of a standard model can be turned into a type of the set model. Of a family model.
Wait, so why do constructors for bool?
Well, because bool has 2 elements, but I could have, it's written like this.
No, I mean the uppercase bool, the next, so that part. So I have. So why does one of these project to the set of 2 things, and the other is only to the unit set?
Yes. So because we need to define, I guess maybe you can define true and false in this model. We can rename. Okay, and so true should be for every gamma TM gamma bool. Okay, and what happens in truth is that the choice between true and false is made in the first component, and then the second component. Well, the choice was already made, so we don't really want to add another bit of information. So another way to look at this is to define the second component to consist of a Boolean as well. But then we also want to say that okay, so we say that the second component consists of a Boolean, but we also want to say that this Boolean is equal to X. And and actually this is related to other definitions of the family model. There are ways to define there's another way to define the same to define data that is equivalent to this, but is written in a way that is a bit different. And there it will be more uniform between the 0 and 1 levels, but we add some equality constraints that look like this.
We need 2 components because that's how it becomes a family. I just remembered. Okay.
Yeah, I guess. Yeah, it would maybe be better if everyone could see the whole file all the time. Yeah, so I was saying that if you have any type of a standard model, so here this is this A, we get a type of a family model where the family part is trivial, so it does not contain any information. Okay, and the types that you have seen here, so the empty type, the unit type, and booleans, they are all of this form.
Quick suggestion: you could try on the right side. You could show the top half file with the definitions.
Okay. Yeah, I can do this. Okay. Should I switch them, or is it okay to have this one on the left and this one on the right?
For me, it's all the same.
Okay. Okay, so the types that you have seen up to here are just of this form. They're just obtained by taking a type of a standard model and lifting it to a type of a family model using this from set. So how do we define a type that is not of this form? Well, we can define a type A. where the first component is, for instance, has one element, but then the second component no. But then there is no element at the second level. Okay, and this type A will be quite interesting because yeah, it turns out that it can be used to prove. Yes, so the law of excluded middle does not hold for A in the family model. So what is the law of excluded middle? It's the principle that says that for every type A, either A is inhabited or not. Okay, so we will try to prove that there is no term Tm in Tm of gamma, well, Tm of the empty context A or not A. Well, okay, but before this, we need to be able to define negation and some types to understand what this means in this model. But intuitively, this happens because in this type A is inhabited in the first level, but not in the second level. And this will imply that, and if you want to prove that either A or not A, we need to make the same choice at all levels, and this will not work with this type A. Okay, so okay, maybe let's first define some types.
Sorry, I have a question about the previous part about the making the same choice. So it's unclear to me what values of type A would look like, and so I'm just not seeing how
So
the not A side would fail. Like, what exactly is to have an A at hand?
So there is no term of type A, but A is not the same as the empty type.
Because I mean, if I just take a cursory glance at it, it looks as if I could feed it. If I did have an A, I could get 0 out of it by just feeding the second function unit.
No, because this is a. I mean, if this is a family, this is not an. So if you have a term of type A, then yes, you get 0.
Yes, but then doesn't that mean I can make a not A?
No, you can make not A externally, but it's not the same as not A internally.
Okay.
But we need to define not internally to understand what this means.
Right, and I guess we would also need to know what the induction scheme for A is, because otherwise, what could like we don't really know what we could possibly.
So A is not an
inductive
inductive type, so there's no induction scheme for A. But maybe I will define some types and not, and then we'll see if you still having some question.
Okay.
But okay, so to define some types, we need to define some types into meta theory. So maybe I need a different notation. Okay, and the thing is that Booleans, so we should have isomorphic to top plus top. And in the type of Booleans, we have made the choice between true and false in the first component, and there it will be the same. So in the first component, so needs to quantify over the context. So in the first component, we may give a choice between the left side and the right side of the sum type, and there I really need some so what's the syntax for
lambda and opening brace patterns and closing brace at the end?
Yeah, I put an example earlier in the chat. You can use the.
Okay.
But I think the pattern also works inside the. You also have to put the pattern in parentheses.
it seems to work. Okay, so it's we can move this here. Okay, so to define some types, what we do is that on the first component, we make a choice between A0 and B0, and then on the second component, depending on the previous choice between A0 or B0, we have an element A0 or B0 of the corresponding types. And then we say that the family is either A1 or B1, depending on this choice. Okay, so there you can check that we have bool equal to top plus top, or isomorphic to top plus top. And we also need to look at well, to define so the negation of A should be the type of functions from A to the bottom type. So we need to define the type of functions. And so the first component is just the same as in the set model. So it's just a dependent function from A0 to B0 over the context. And the second layer is also a dependent function, but with components. But why don't the first layer we have a function from A0 to B0? On the second layer we have a function that depends on both A0 and A1. This barely fits on the screen. Okay, and now we can try to define a term of type A or not A. Well, I need to define the empty context first. Okay. And what happens when we define this type is that on the first component, we need to make a choice between giving a proof of giving an inhabitant of A at 0 or an inhabitant of not A at 0. However, if we can, because this only depends on A0, we can only see that the only choice that you can make here is to give an inhabitant of is to say that A is inhabited. Okay. So there we have no choice. And then what we need to do on the second level, we need to give. So if I normalize this, we need to prove that the empty type is inhabited. And why is this? So if we look at the definition of so if you look at the definition of some types, because on the first component we have picked the left side, on the second component we need to give an element of the family of the left side. So we need to give an element of A1 over TT, but I can move the definition of A here. I can also move this thing back here. Okay, so this means that because we have chosen the left side on the first component, we are forced to stay in the left side for the second component, where we cannot give an inhabitant. Okay, so informally, what we would want to do to define this is to say that for the first component, we choose the left side because the first component of A is inhabited, and for the second component, we choose the right side because the second component of A is not inhabited. But we can, because some types in this model force you to choose the same side for both components.
But externally in the meta theory, we could prove that defining such len is not possible, right?
Yes.
Okay.
Okay, and this implies that that the lawyer is not in the syntax of type theory, because if it was provable in the syntax, we could get a proof in any model, but we have shown that there is a model in which there can be no such proof.
You're missing a negation. An important one.
Where?
In the last line. This implies that LEM is not provable.
Yeah, thanks.
We could also, why don't you prove that now that there is no term of that?
Okay, I can, that there is no term. So yeah, then yeah, so we can prove what should be the name of this proof? Yeah. Okay, so I prove that assuming that we have here, so assuming that we have such a term, we derive a contradiction. Okay, and there are two cases. So, and what happens is that we have okay, so this A0 be either in the left or in the right component. But so I need to look if A0 is in the left or right component. I do this using well, dependent pattern matching in Agda. Will this work? Yes. Okay. In this case, we learn that A0 is in the left side, but this means that A1 has to be okay, so in this case, we should learn that A0 TT is equal to to this, but this has not been learned by Yagda, so we will need to do some. For instance, we can remember some equality or use some different way to get this. But morally, this A1, it's in the empty context. We need to apply it to elements of the unit type. But in this branch, we know that A0 of TT is in the let branch, so the type of A1 TT reduces to the empty type. So this is well typed up to some equalities. And on the second side, we have y in A0 to the empty type by definition of not, but A0 is unit, so we can just apply y to the unique element of unit type to derive an element of the empty type. Okay. Yeah. So so this is almost a full proof. We just need to convince Agda that it's correct. I think it doesn't work because A0 depends on the unit type, and because of this, this with pattern doesn't work.
I think an easy way, or a relatively easy way to solve it would be to not use the pattern matching lambda, but some other function, and then you can introduce the other function in the width matching later.
Yeah, you could use the inspect.
Something like that. And the problem with pattern matching lambdas is that they don't behave well because they don't really have an identity.
But yeah, and another way is to just look at the types of A0 and A1, remove remove the units, and then maybe it should work. Maybe the units don't matter. Well, okay. Anyway, I don't want to fix this now. Maybe probably I will do it before uploading this file. So are there any questions about this? Okay, so what should we do now? One thing that we can do is to look a bit more generally at preshift models.
What about parametricity? And if you define universes, then we can show some parametricities about the identity function, for example.
If we define the universe in the family model?
So if you define universe, then the polymorphic identity function has some parametricity statement. So in the model, it's always the identity function.
Okay. Do I need to shift universe levels everywhere?
enable type in type.
Maybe this works. Okay, so let's define the universe in the family model. Okay, so U the type in the context. So, I mean, is this the universe in the family model? Because I didn't.
Yes.
Okay. Yeah. So on the first layer, it's just the universe in the set model, and on the second level, it's the family of families over an element of the first universe. Okay, so we need to define the decoding function for the universe. Well, and essentially it's just well, essentially it doesn't do anything. But well, implicitly, if we don't use the type in type, it will raise the universe levels of components A0 and A1. Okay, and if we want to define the polymorphic entity functions, we first need to define pi types, but we already have functions, and pi types will be similar. Okay, so now this zero depends on A, and B1 depends on A0 and A1. Okay, so yeah, pi types are the same as function types, just with some more dependencies. And the polymorphic identity function should depend
You can also write it out explicitly. I mean the variables here.
What do you mean?
I mean, so we don't have to define Q. You can just write it out here.
Yeah, but yeah. We still just okay. We can define this identity function. X, so it will be the identity function on both components. Okay. Yeah. So what is there to say? So this is the identity function, the first component, and
So now what we can say is that so basically the statement is that if you take any term with this type in the syntax, then the standard semantics must be the identity function. Because here we have this family interpretation, and then we can show that if we have the second component, which says this function preserves all the predicates, then this implies that the first component must be the identity function. And then we can combine this with the evaluation of syntax. So it says that this
if as a predicate we pick equality or something like this.
Yeah, if we, as a predicate we can pick that the input is equal to a particular element of the type. And because it preserves as predicate, then it says that whatever the output must be the same.
Okay, so we could try to so if we have
but isn't this a bit circular, because we are going to pass a particular predicate, and we show that, okay, in that case that proves that it is the identity function, because it has to be like meta-parametric in the predicate or something like that. Like, just
no, so you can assume any type and an element of that type, so that those are the assumptions. And then you can show that this ID, if you apply to that particular type and that particular element, then it's equal to that element. And there's no other way that it can have an output.
right, but then
So you can say this internally and prove it.
But I mean, what if that identity function looked at the predicate and only did this if the predicate was this equality predicate. I mean, I understand why you can't do that, but isn't that just because of meta-parametricity?
No, I don't think. So there's no meta-parametricity here. So we are not using parametricity in the meta theory. So this would also work in some non-parametric meta theory. So we are only using that the TM gives a, so the pi type basically gives us a proof that this function preserves all predicates, and that comes from the model. So we are not using meta-parametricity.
Right, but I mean, just because it preserves that its input being equal to some x, it preserves this property, i.e. the output will always be also equal to x. But can't it be that it only preserves this, like for every x it would be like a different way of preserving that?
I mean, in the meta theory, if we have UIP or proof irrelevant equality, then we don't really care about this. There is only one way of preserving an input by equating it to the output, right? If we have UIP.
Right. Okay. But it, okay.
Yeah, so here we say that if we have any TM of this pi type, then we can show that the first projection, the first component, is always the polymorphic identity function. And then we can do that by first we assume that we have some type and we have some input, and then we choose the predicate to be the predicate which says that it's equal to the input. And then we get that the output must be also equal to the input.
Oh, I think I got it. Okay, so okay. I think I get it.
And then we can also combine this result by evaluation of the syntax. So if we have something which is syntactical and has this type, then we can evaluate into this model. And then we get that even in the syntax, it is not possible. So it is only possible in the syntax to write a function with this type, such that the standard semantics is the identity function. Because here, like the first projection everywhere in this model is just the set model. So this says us that even in the syntax, you can only write a function which is in the set model, the identity function.
I think you can just finish this. So you also assume an element of U or a type, and an element of it, and then or a TM of MTU. And
so this will be the statement of parametricity, but I cannot fully state it because I have not defined application, for instance.
Yeah.
So if A is a type and X is in, so A is an element of the universe and some X is a term of type A. Then we have we can at least prove something like the application of this function f to A and X. So if you apply f to a and x, and we only look at the first components, this will be the same as the first component of x. And the way we do this is that we instead of applying
the both components work, so you don't need to write 0. You can really do it completely.
Okay.
Yeah, that works.
And the way this works is that we replace, we actually apply f to some thing that is not a, but that is in some sense a restricted to x.
Are we sure that the second component works as well?
I don't think so.
Yes, because x, so small x already has a witness that the second component for a works. And
maybe this works if
you can try it. It works.
We are in prop, but okay.
I don't think it works.
I think this won't work. To a prime, so a prime 0 will be the same as a0.
I mean, it shouldn't work for the second component because then we quantify over all predicates and we don't have anything to use. So we can only use the second component to reason about the first component, right?
And the second component, we completely discard the second component of a, I think. Then we can prove that we have x prime an element of a prime, where x prime 0 is x0 and x prime 1 is the reflexivity proof of this equality. And the second component of f a prime x prime will be a proof of a prime 1 x prime 0, and this is a proof of x is equal to this is a proof. This is not. This is. Okay, so the first component will be a proof of a prime 1 at the first component. The first component is this, but it's also equal to the same one without the primes. So I think we don't get an equality between the second components unless we restrict the model to prop valued families. And so the consequence of this parametricity proof for the family model is that any identity function defined in the syntax becomes the identity function in the standard model. Because so if we have
maybe it's a bit more precise if we say that any function with this identity function.
Yeah. Any function with the type of the polymorphic identity function defined in the syntax so the syntax is this model and the standard model is this model. Then if I have f a term in the syntax of this type, then I get we get also copies of, we can interpret f in, and so what happens is that we have but what should be the names of these? We have some interpretation from the syntax into the family model and into the set model. And you also have some morphism from the family model into the set model that forgets the sequence components. And this one, we can do some difference notation, but actually we can just, because there's a unique morphism from the syntax to the set model, we know that this one is the same as the composition of these two. Okay, so now if you have some term in the syntax, we get some term in the family model, and we also get some term in the set model. And well, we know that the term in the family model satisfies parametricity in the family model, which means that its first component is the identity, and this says exactly that this one in the set model is the identity. So maybe you can look at some simple variants of the family model. So one way is to add more dependencies. For instance, we have gamma 0 and gamma 1, but we can also add some gamma 2. And if we do this uniformly for everything in the type theory, we'll still get a model of type theory. And another way, instead of extending in this dimension, is to add more dependencies to this, to gamma 1. Okay, so now gamma 1 depends on two elements of a base context, and I don't know what's the name for this model, but while the family model was related to unary parametricity, so where we have a predicate over things, this model is related to binary parametricity, where we have a binary relation between terms between elements of a type.
So I have a question regarding that. Usually, like in the usual settings of parametricity that I normally work with, we take an equivalence relation instead of an arbitrary one. Can we do the same thing here, or is there a reason we don't do the same thing here?
So if we take right, yeah. So actually, in the end, we want to do the same, I think. So
I think if you take an equivalence relation, then this becomes the setoid model.
Yes.
But it is a lot simpler to say that we just have any relation. And it can be a proof relevant relation as well. So, I mean, it depends. If you only want to show parametricity, then we get the usual free theorems by only saying that we have a relation. And it is a lot simpler to define that model than to define the setoid model together with universe, especially.
Mm-hmm.
That makes sense. Thank you.
Okay, yeah, I think we can also look at the reflexive graph model where we don't ask for this relation to be an equivalence relation, but we want it to be reflexive. And this is still yeah, so this is still quite easy. But if we want to add symmetry or transitivity, then we somehow go out of this class of models, and things become more complicated. So I can try to discuss a different way to define this model, where well, we still have gamma 0 and gamma 1, but now we have gamma 1 does not depend on gamma 0 directly, but we have some function from gamma 1 to gamma 0. And so this is equivalent because I can give the two functions. So on one side we use a sigma type to replace gamma 1, but replace the family gamma 1 by the set of pairs of elements in gamma 0 and gamma 1. And then for the for this function, we project the element of gamma 0 from this pair. So this is the so the correspondence in type theory between families and I guess yeah, vibrations, or so a definition of family where dependencies are encoded by some additional function. And the problem is that to go in the other direction, we need to introduce some equalities. So we can define the identity type. So in the other direction, we need to introduce these equalities. So we say that the family gamma 1 consists of tuple of pairs where we have an element in this bigger gamma 1 whose restriction to gamma 0 is equal to the element of gamma 0 that we have. Okay, and well, so we can define the whole family model with this definition of contexts and use similar definitions for substitutions, types, terms, and everything. But then there will be some equalities like this everywhere, and we actually needed to use these equalities and prove some equalities and so on. So it's so in particular, it's much more complicated to define it in Agda.
So let me see that I understand. Like this makes this into some category of pre-sheaves over a category which has two objects and one arrow between them, or
Exactly.
something like that.
Exactly.
See.
So
Yeah, that explains why you said it was a pre-sheaf model. Okay, it's making much more sense now. Yeah.
So their contexts are pre-sheaves over the category with two objects 0 and 1 and one morphism between them. And the reason why we are able to use this simpler definition for this pre-sheaf model is that this category is very nice, and this category is directed, so we can mark some of the morphisms of this category and say that the equalities that are typically found in a pre-sheaf model will be replaced by dependencies for these special morphisms. But it's not I guess I can give some quick description of a pre-sheaf model. And in general, so we have some parameters. The set of objects and the set of morphisms or arrows between two objects. And in a pre-sheaf model, we'd have a set like this for every object in this parameter, in this set of objects. And we'll have some restriction function for every element of the set of morphisms between two objects. And then we also need to add some compatibility conditions. Okay, so actually for some nice categories such as this one, we don't need to add any equalities. And for some categories that are even nicer, we can represent everything using dependencies instead of restriction functions. Again, why are pre-shift model interesting? Well, so we have seen, so all of these models are small pre-shift models. So for some specific choices of categories, pre-shift models can encode, for instance, things related to parametricity and or similar things. And well, in general, any construction performed in a pre-shift model will be compatible with the chosen with the chosen category, base category. Yeah, so pre-shift models are a way to ensure that all constructions automatically respect some things.
So the two things we demonstrated today using this family model, they're closely related, right? Like if excluded middle doesn't fail, then we don't have parametricity. Isn't that right?
If exclude, I know that excluded middle is related to parametricity. Yes.
Well, I should be able to decide what set I'm looking at, right? By just saying, well, let's see if A is equal to NAT, and then do something different.
Yeah, exactly. Right? So so if the law of excluded middle holds, then parametricity will fail in some sense.
I think it's provable in the syntax as well.
Yes, if you have any things in the syntax.
Middle, then internally parametricity for the polymorphic identity function. It's a simple form. It fails, and then it fails.
It's very easy. It's you just with lem A equals NAT, and then that should do it. You'll be able to define in the syntax a function that's not the identity on NAT, but the identity on everything else.
Yeah. So in principle, we can also use this to only do this only show the refutation of excluded middle in the family model, and then from this syntactic proof to get that we have parametricity if we have excluded middle in the meta theory as well.
Wait, how does that work?
Oh, okay. I'm not sure.
I understand the other direction, right? Like if we show that parametricity holds in this model, then we can show that excluded middle doesn't hold. But the other direction, I'm not so sure about. Like, that sounds.
I think the other direction might work in homotopy type theory for some suitable definitions of.
Oh yeah, right. The other direction.
Excluded middle. I know it has been studied. Yes, so I know there is something about this on the homotopy type theory blog, and I pasted it in the Teams chat.
Yeah, that's very nice. It proves both directions. It's brilliant.
Balázs? Your hand is raised.
That was an accident. I don't know how it happened.
Okay, maybe we can decide what we should do next time.
Yes. What about the pre-shift model?
Yeah, I guess. Yeah. Yeah. So I'm looking at what was planned in the first file, and I see pre-shift models and the canonicity model, and maybe a normalization proof. So yeah, canonicity would not require pre-sheaves.
Yeah, canonicity could be also the next one. But maybe if you want to do both, then the ordering, I don't think it matters because they are independent.
Yes.
Hey, sorry, I was away a bit. Are you talking about what's happening next time?
Yes.
Yeah, so I think we could continue with pre-sheaf models, no?
Okay. Yes.
Like general pre-sheaf models, or what? Or was there any other suggestion?
And there's also canonicity that can be done either before or after pre-sheaves.
Yeah, but you've already started talking a bit about pre-sheaf models, so we can do it. I am doing it next week, right?
Yes.
Yeah. Okay. Yeah, so, yeah, okay, I can talk about pre-sheaf models and Yoneda and yeah, we will see like how the pre-sheaf model combines stuff from C and stuff from the meta theory and this kind of stuff.
Yeah. Maybe I can stop the recording.